Hey everyone, it is 10 after or 40 after, depending on where you are at in the world. We are going to have the second talk of our second session and our last talk of the day. And again, we are returning to an emerging researcher who's working on doctoral studies. This is Marvin Roski from Leibniz University in Hanover, who's done some work in data mining, learning analytics, and I picked up some universal design for learning in terms of previous work, which is exciting things trying to think about how we can create learning environments for all students. So I'm going to turn it over to Marvin. Please, as always, use the chat to drop your questions, and we'll be back in a few to do questions. Marvin, the floor is yours.
Thank you very much. I hope everyone can see my slides and understand me. So welcome to my presentation, exploring data mining in chemistry education, learning analytics in the web-based learning platform i3Learn. So as already mentioned, my name is Marvin Roski from the Leibniz University Hanover in Germany, and I'm here in the Institute of Science Education. So I'm currently a PhD student, but I submitted my thesis a few weeks ago, so maybe in the future, no student anymore. So I'm also part of the PhD program LearnMint, where we are a total of 15 PhD students. Half of us comes from the STEM education area and half of us come from computer science. And we are working on data-driven learning and the integration of AI in the STEM field. So one of the core idea of my project is to expand chemistry education research by using technological advances, including AI, to expand the scope of action. So what do I mean by that? In chemistry education research, an incredible amount of testing instruments have been developed to gain qualitative and quantitative insights into learning, and technological advances have made it possible to expand the resources of chemistry education research to include not only product data, such as the results of an assessment, but also actual process data that can track the learning of large samples to the second. So what are the take-home messages from my presentation? First of all, I would like to describe the web-based learning platform i3Learn, which we developed to introduce learners to the topic of ion bonding, but is also suitable for mining data for AI and learning analytics applications. And in particular, I will talk about the different perspectives that we considered and that had an influence on the design of the platform. And second, I would like to discuss the mined data, which is collected in form of log files and describes possible applications using two examples. One is an AI-based dropout prediction, and the other is a cluster approach to analyze usage behavior. So what are some potentials and challenges for a web-based learning platform designed to collect data for learning analytics? And in a world of multiple crises, web-based learning may become more important in the coming years. Web-based learning also has the potential to enabling independent and self-regulated learning, even with more complex topics, and it can ensure accessibility for all learners through the use of digital resources. Also, AI in science education is an interdisciplinary field of interest, but often lacks of a subject-specific educational grounding. And we need within web-based learning to collect fine-grained interaction data for AI and learning analytics applications. So not only product data, but also process data such as clicks and processing time. So our web-based learning platform i3Learn is for chemistry classes. It's on the topic of ion bonding, as already mentioned, and it's for grade 9 and 10. It has around about 180 minutes of learning time, and the teachers are free to decide how they want to use i3Learn in their classroom. And many considerations have gone into the learning platform, and the easiest way to describe them is to look at the learning platform from different perspectives. So the first perspective is the arrangement of the learning chapters or what the learners mainly see. So I am bonding is part of the curriculum of the 9th and 10th grade in our federal state here in Germany and is used to define the content area. However, I am bonding is a really challenging subject for learners as it requires a lot of prior knowledge and the extensive learner conception. For example, ions exist as molecules, or ion bonding is based on the division of electrons. These points have actively influenced the arrangement of the learning chapters. So at the beginning of the learning platform, learners have the opportunity to voluntarily repeat prior knowledge for the topic of ion bonding, such as noble gas configuration or electron transfer. And this is followed by the middle part of the learning platform, which corresponds to the common learning goal. So in other words, what all learners should know according to the curriculum. And finally, we have the third part for advanced learners. They have there the opportunity to deepen their knowledge and achieve the extended learning goals. So with this, we have clarified the rough structure of i3 Learn by arranging the learning chapters. However, this does not yet fully address the chemistry education foundation. So although the general frame has been defined, it's also necessary to assign a chemistry education foundation to even the smallest parts of the learning platform. And to do this, we have broken down the topic of ion bonding into so-called knowledge components, which in their entirety represents the topic of ion bonding. And these knowledge components were formed on the basis of the curriculum and the learners' conceptions of ion bonding. So we have in total 7 knowledge components, which breaks down the topic of ion bonding. And this includes, for example, knowledge component 1, knowledge about the structure of atoms and ions, or knowledge component 2, about the formation of ions as an electron transfer. And with this new perspective, we can add the chemistry education foundation, can we assign to the contents of the individual chapters to one or more knowledge components, and thus also track which knowledge components the learners have worked on. So as you can already see here, we are now expanding the architecture of i3 Learn with this new perspective. The third perspective is inclusive education in i3 Learn. And to achieve this, we use the framework of universal design for learning. And these are concrete suggestions aimed to minimizing barriers to learning. Minimizing learning barriers is a major part of the discourse in inclusive science education research. And the definition of inclusion we use in this project is in the sense of a broad understanding that values diversity and aims to remove learning barriers and enable participation for all learners. So the guidelines, or the UDA guidelines, are a collection of suggestions to make learning accessible to all learners, regardless of their prerequisites. So the guidelines are divided into 3 principles: provide multiple means of engagement, provide multiple means of representation, and provide multiple means of action and expression. So unfortunately, I do not have the time to go into all of the details of the UDA guidelines, but I can show you what guidelines we have realized in i3 Learn to give you an idea of how this can look like. So the implementation of the UDA guidelines is always voluntary. This means the guidelines can be implemented, but it's not mandatory which ones and how many. And in i3 Learn, for example, we offer multiple representations so learners can choose between a text or a video, or we have a customizable interface or a read aloud function. And this perspective now adds further details in the architecture of i3 Learn. For example, here in the microstructure within the chapters, the possibilities to choose between a text, a video is now here added. So last point is the collection of data for AI and learning analytics applications. And what data do we collect? The short answer is many. So in principle, the data can be divided into personal informations and interaction data. And the personal data are mainly things that are collected in a pre and a post test. and the interjection data is data that are generated through the use of the learning platform. So on the right side, you can find what I call process data at the very beginning of this presentation. And with a view back to the architecture, now a pre and post test is added, and the pre and post test also includes a subject knowledge test. So the individual items of the test can be assigned to the knowledge components so that changes can be evaluated here at a very detailed level. And what is not directly shown here in the architecture is the fact that the process data is collected everywhere. So in the learning chapters, but even when the learners provide demographic information in the pretest, every click is recorded to the second. So we have 580 learners who worked with i3Learn in total. There are 27 classes, and we have an extensive pre and post test, which in addition to the subject knowledge tests, also measure things like reading ability, cognitive ability, and a lot more. So in total, we have collected a database of almost 500,000 log files. To briefly summarize this part, so we have many factors that influence the architecture of the web-based learning platform to provide a foundation for chemistry education, accessibility for all learners, and the ability to collect comprehensive data for learning analytics. And we implemented this by building our own learning platform from scratch using the content manager WordPress. So we did not use some existing systems like Moodle, but we created our own platform. And now in the second half of the presentation, I would like to present two studies in which we worked with this process data. So the first one is dropout prediction, and AI-based dropout prediction is a well-known application in larger and more long-term learning opportunities, such as massive open online courses, MOOCs, and we have here the possible usage options in the classroom for having an early warning system or informations for a teacher dashboard. So for this presentation, I've selected two research questions from the paper that I would like to address here briefly. So can AI-based dropout prediction models be effectively adapted to a shorter and more formal learning setting? And the second question is, which features play an important role in AI-based dropout prediction? So to do this, we have defined a total of 6 dropout levels, which we would like to predict the dropout and which can be located in the already known architecture of i3Learn. And we used all the data or the existing database and use these features to predict the dropout to the different dropout levels. And to do this, we use the library PyCaret to test different features and different machine learning models to predict whether learners would reach the different levels or stop learning early. And what we can see when we compare the results is that personal information and interaction data at different dropout levels predict dropout to different degrees. So here you can see the F1 scores and the model that performs best. So while personal information is better at the beginning, we see here, for example, for level 1, we have a K nearest neighbor machine learning model, or for level 2, some gradient boosting classifier. We see that the interaction data is better towards the end, and at the very end, there's some unique pattern where personal information becomes more important again. So all in all, it's possible to predict dropout at different levels in a learning platform like i3Learn using AI, and we overcome the cold start problem with personal information because process data or interaction data is not available at the beginning. So we overcome this with the code with personal information. And the takeaway I want to show here is that in this case, it's not enough to just use data from a pretest, but we also need process data to improve the prediction that leads to better results in integrating AI into chemistry education. So the second study is a cluster approach. and we have the guiding questions to gain insight into the learning behavior. So we ask ourselves the question here, how do learners use UDL guided elements in i3 Learn? And here you can see again which UDL guided elements are available in i3 Learn. And we pursue the goal of gain insight into the learning process and want to create a foundation for an AI-based support system and for dashboards. And from this study, I also select 2 research questions for this presentation here. How can the complexity of data on the usage behavior of UDL-guided elements be reduced, and to what extent do similarities in the usage behavior of UDL-guided elements lead to clusters, and what informations can be derived about the learners? So, as I said, first step was to collect data. We have here our 580 learners and almost 500,000 log files. And in the second step, we prepare the data. This means that we do not use the complete data set and all UDL-guided elements, but we concentrate on multiple representations. So text and video usage, learning tasks with and without help, and on self-assessment. So the focus is that learners have the opportunity to choose freely between different options. So like choosing between the text and the video, and these are the UDL-guided elements we focused here. So in the third step, we use an explorative factor analysis to reduce the complexity in a variable-centered way. And in the fourth step, we discovered 6 different clusters with k-means clustering. With k-means clustering, we have a total of 6 different clusters, and it's also noticeable that the clusters are unevenly distributed. So cluster 1 contains almost 60% of the learners, while cluster 2 contains less than 2% of the learners. So at first glance, it seems that the clusters found are not suitable for continuing, but if we take a closer look at the difference between the clusters, we can see some considerable differences. So, for example, if we look at the average usage time, then we see the cluster 1 with a 60% of learners is a cluster that hardly invests any learning time in i3 Learn. And cluster 2 with just 2% of the learners differs greatly from other clusters. So these are the learners who really invest the most time by far. Also with regard to cluster 5, which comes in second place, and the difference here are over 500 seconds, so more than 8 minutes. And we can take a closer look at the differences by looking at the use of text and video. Here we have the, you can see on the left, the standardized text usage and also the differences between the clusters. So while cluster 2 and cluster 0 invest a lot of time in text, it looks quite different for cluster 1 and for cluster 5. And we also have a different picture when it comes to the video usage. So you can also see here on the left side the standardized usage, and you see cluster 5 really dominates here heavily. So these are the learners in this cluster who really use videos more than the other clusters. So unfortunately, time does not permit us to take a close look at all of the clusters, but we can look at 2 clusters for now. So for example, cluster 3, the cluster description of this cluster is learners with balanced characteristics. So we have not mainly female learners or mainly male learners with balanced characteristics who used text-based learning and tasks with help. So they invest lot of time or quite a lot of time in text usage, but also a lot of time in tasks with help. So they need a lot of time to do this tasks with help or with support. And when we compare to cluster 5, we have here diverse learners who prefer videos and reflect on their learning process. So we already saw that these are the learners who use videos a lot, but we see also these are the learners who reflect the learning in the self-assessments. So all in all, we transferred the usage behavior into human readable clusters again. So we took the process data and made it readable again. And our categorization is based only on the learning behavior and on the process data. So this also means with regard to inclusive education, is there any here who are interested in this area, that we have formed categories again, but these are not based on stigmatizing characteristics, but purely on the usage time. So here we pursued a different idea than in the first study, that we saw that process data can be complemented existing data, such as demographic information, to optimize the prediction. And in this work here, we only use the process data to form our clusters. And what is the outlook of this work? We need to an automated AI-based assignment of learners to the clusters or the digital twins we have here to provide information for a dashboard. And we need to define necessary learning support for each of the 6 clusters. And to summarize the whole presentation, the development of a web-based learning platform for chemistry education requires integration of different perspectives, such as grounding in chemistry education, or the possibility to collect extensive process data. And what I also shown is learning analytic approaches make it possible to predict learner behavior and identify behavior patterns based on the process data. So I hope I was able to show you, with the help of the technological advances, chemistry education research can use new resources and further explore and improve learning for all learners. And at last slide here, I do a little advertisement for the paper, so I saved time. I've not gone into all of the points of the paper, but if you're interested, you're welcome to read them. So the first paper is about how to build a web-based learning platform with WordPress, and the other 2 are corresponding studies I also mentioned here in this presentation. And there's also here my email address. If you have any further questions, please reach me out. And thank you for listening, and thank you to my colleagues.
Thank you, Marvin. Insightful work as to how we can take things from a learning system and use them to think about our practices. I want to start off here with encouraging people to put